Okay, everybody, we are now entering into a new unit here where we have now learned all of our derivative rules. So now we can talk about how to apply them in finding extremum like maximums and minimums, either graphically or from the equation, which we'll take a look at both situations here. You should have a new foldable for this particular lesson that you got the day before. Because we're going to be adding a couple theorems, possibly 2 theorems today. So take notes in your notebook. I got some pictures, some graphs to draw, and remember you can always pause me and go back and rewind and zoom during this lesson. All right, so let's take a look. So if I've got a mileage of a certain car, and the mileage is given by this certain equation, where the mileage is what the output is, and the velocity is the input, so m of v. So knowing a certain velocity, I can tell you what the gas mileage would be at that particular velocity. Obviously, a very overly simplistic model here of this cubic. The question is, what speed or what velocity should I drive to get the best gas mileage? I want to get the greatest gas mileage here. So what do I have to do? Well, one thing is I can take a look at what the graph looks like. So if I graph this on my graphing calculator, maybe you should too. I had to play around with the window to enlarge the window a little bit, increase my y max and my x max. And you can see that there is a point in this graph where it is up at the very top. This would be my greatest gas mileage, and whatever the x value is at that point would be the speed that I should be going. So I did on my calculator a second calc max, remember left bound, right bound. And so I get a maximum at that coordinate, 38.6 and 32.12. So what is what? What does the 38 represent and what does the 32 represent? Well, it says then the car will approximately get 32 miles per gallon when the car is driven at 38.6 miles per hour. I guess I didn't give units here, but those were the units in this problem. So 38.6 was the actual gas, the speed. That's your x value, and the output value, the y value, is 32 miles per gallon. That's your gas mileage. So in this case, we're looking for the maximum, but also notice that at the top of the curve, that maximum has a slope of 0. So are there ways for me to get slopes of zeros? Yeah, so that's what we're going to take a look in a little bit, is I could set the derivative of this cubic equation equal to 0. It's going to give me a quadratic. And so that quadratic, if I set that equal to 0, should give me 1, possibly 2 zeros. And I would then have to determine whether or not it's a maximum or a minimum. That's what we're about to enter into here. So absolute or global extremum, maximum minimum values, are maximum minimum values on a curve. So we're going to talk about some terminology here about types of extremum. So we can have absolute or global extremum, or local or relative extremum. So extremum can be at any different points on the graph. So let's say I just have this big open interval of the parabola. So where are my maxes and mins? Well, the maximums, yeah, are heading up to infinity, and we don't identify infinity as a maximum value. So in this case, the graph only has a minimum, and that is its absolute minimum value is 0 at 0. It's also what we're going to call a relative or a local minimum value as well. Locally around this area, that is going to be its minimum value. No absolute max. What about this? Now I'm doing it on a closed interval from 0 to 2. Where's the absolute max and where's the absolute min? Well, yeah, absolute min or local min is happening right there at 0 at the value of 0, and the absolute max is over there on the right, with the value of 4 happening at 2. That's also a relative maximum. So maximums can happen on the endpoints themselves. Well, what about this situation, where one side is closed and the other side is open? So where is the absolute minimum value? Well, it doesn't have one, because that's not inclusive. I'm not including the 0. So this graph on this closed interval or in this domain has no minimum value, as strange as that feels. but it does have a maximum value. It has a maximum value of 4 at x equals 2. We'll take it one step further. What about this? Yeah, kind of crazy to think that there's on this closed interval here, or open interval, I should say, is no minimum and no maximum values. It's kind of strange, but so dealing with the endpoints are going to be pretty important about whether or not I'm going to be checking those endpoints for maximums and minimums. Obviously, maximums and minimums happen somewhere in the middle, like in a parabola, but check our intervals as well. So our first theorem here is called the extreme value theorem. And what it basically is doing is guaranteeing whether or not a graph is going to have a maximum and minimum value. Well, the extreme value theorem says, okay, if you have a function that's both continuous and on a closed interval, meaning I'm including those endpoints with the brackets, not parentheses. So if the graph is continuous on a closed interval, then the extreme value theorem guarantees that you're going to have a maximum and a minimum value on that interval. So as long as you have closed endpoints, filled in circles on the ends, and the graph is continuous within that interval, you are getting a maximum and minimum. So this goes on our foldable. Extreme value theorem on the outside, and then this description or this definition on the inside. And you can pause me now to go and write that. Making a note here, sometimes this is called the max-min value existence theorem. It's basically guaranteeing the existence of a max and min. Doesn't mean that if these conditions aren't met that there isn't a max or min. This is just guaranteeing that this will happen. So I have situations like this. Closed endpoints, I'm filled in circles on the ends here, continuous within there, so there is a maximum and minimum happening. And obviously it's at the peak in the valley here. That's where your maximum and minimums are happening. Well, in this case, I've got closed endpoints again. The graph is continuous on this interval, so therefore the maximum and minimums wind up happening at the endpoints. And you can have a combination of the two. I'm including the endpoints, but here the minimum's happening at the left endpoint, but the maximum's happening at an interior point. So it can be a combination of the two different types. So again, I've been throwing some of these words around. Local or relative extremums. Local or relative are the maximum within some little defined area within a local space within the graph, but absolute or global extremum are the absolute maximums and minimums where they occur and what those values are on the whole interval. So we have absolute or global max and mins, and we have relative or local max and mins. And our graphs can be a couple of difference of eaches. So let's maybe kind of look at those differences. You'll see this terminology, either absolute or global and relative or local. You want to make sure you have those descriptions down. So let's take a look at the graph. So some kind of crazy, funky graph here. So where are the maxes and mins and what types are they? Well, okay, way over here on the very left, that is an absolute minimum or a global minimum, but it's also a local minimum or a relative minimum. So around here, around this part of the function, around this little region, that is the minimum value within that region locally, but it's also the lowest value of the entire function. Well, what about this peak right here? Yeah, that's going to be a local maximum. It's not the absolute or global maximum, but local or relatively, that is a local maximum. My next one? Yeah, it's a local min or a relative min. Not the smallest value of the function, but locally it is. What about this sharp point right here? Yeah, that's an absolute or global maximum and also then a relative maximum as well. And the very last one to check is the far right of the graph, the right endpoint. Well, the graph seems to be coming down. That is a minimum value right there. The values around it locally are greater than that value. So that's a local minimum. So local or relative minimum. Now, take a look. So not only do the maxes and mins happen at the endpoints, but those local maximums within the interiors, look what kind of behavior I have. I would have a slope of 0 and a slope of 0 on those two, but the sharp point over there, that's got a slope that's undefined, but that's where the maxes and mins occurred. They occurred where my slopes or my derivatives are either 0 or undefined. So we can say that local extreme values, if a function has a local minimum or a local maximum at an interior point, not the endpoints, then I know that the derivative, and the derivative exists, then I know the derivative must be equal to 0. I don't know if this is worthy on a foldable. It's definitely worthy in our notebooks. But again, so if I have a function and it has a local min or a local max within the interval, so somewhere in the interior, and the derivative exists, I know that the derivative must be equal to 0. If the derivative doesn't exist and it's a max or a min, then I know that the derivative must be undefined and it must be some kind of a sharp point. The more important thing here is that critical points, places where we want to determine where their maxes and mins, are places where the derivative is equal to 0 or where the derivative does not exist. This is worthy of a foldable door. So on the outside, critical points, and only inside. Critical points are points where the slope is 0 or where the slope is undefined. Those are places that become possible, not guaranteed, but possible maxes and mins, which we will explore. Notice max and min points in the interior of the function always occur at critical points, but critical points are not always maximums and mins. If you think about this for a second, is it possible for the graph to have a slope of 0 but not to be a max or a min? Think about graphs that have slopes of 0 that aren't maxes and mins. What comes to mind? Yeah, I'm thinking of a cubic function, just the basic y equals x cubed. There's a slope of 0 right there at 0, 0 at the inflection point, but that is not a max or a min. So critical points are not always extremes. Here's my example. So just because I have a slope of 0 doesn't mean that it's going to be a max or a min. So that's not extreme. And about in this case, like x to the 1/3. There, the slope is undefined. It's got a vertical tangent line. Well, that's not a max or a min. So just because the derivative is undefined doesn't mean it's a max or min. It means it's a possible max and min. It's a critical point, but not all critical points are maxes and mins. So I'm going to have you do a couple homework problems in the assignment, but this is what the first set of problems are going to look like. They're going to look like what are the maximums and minimums and where they occur. So for instance, number 1 here, I've got local minimums and absolute minimums, both at -2 and 2. And I've got a local and an absolute maximum at 2. And you're just going to be listing those. Just be careful with some of these that have open circles. Remember, you cannot determine them at open circles. Like in number 3, I know it's hard to see, but at 2, there's an open circle at 2, so no min at 2, but there's an absolute and relative or local max at 5. So you'll see some of those. And in this case, the next subset of problems that you're going to be doing are finding the absolute maxes and mins and where they occur. So obviously in number 5, the absolute max happens at B, and the absolute min happens at C2. And the question is, did the extreme value theorem guarantee that? So in this case, the function had closed interval and it was continuous. So the extreme value theorem did guarantee that I was going to get those maxes and mins. So for sure. Number 6, closed and continuous. So yeah, the extreme value theorem says, hey, you are going to get a absolute max and min in this interval. Absolute max occurred at C and the absolute min occurred at B. So you have some of those questions coming up. One I want to take a look at is what happens when you have equations. Let's talk about equations and how you manipulate the equations to find these maxes and mins. So function I want to explore is f of x equals x to the 2/3, and I'm going to close it on a closed interval from -2 to 3. All right, so what do I do to start finding my possible maxes and mins? Well, you find the critical points. There are the sort of places where the derivative equals 0 or undefined, so I guess what we got to do is take the derivative. Simple little power rule here, and I'm going to suggest maybe converting this back into a rational function. It's not a rational, but a radical in terms of radicals. So I hope you're all okay that this is the same as 2/3 cube root of x. A negative exponent throws into the denominator and the 1/3 power is a cube root. So I'm interested in when the derivative is equal to 0. So in order for this fraction to equal 0, the numerator would have to equal 0. We've done this with some of our implicit differentiation problems, where this tangent line is horizontal. Where is the tangent line horizontal? When do I have slopes of zeros? Well, the answer is nowhere. because the numerator is always going to be 2. So there are no places in this function where the slope of the tangent line is equal to 0. But remember, where maxes and mins can also occur is where the derivative is undefined. So where the derivative is undefined is where the denominator equals 0. Well, where does that happen? Well, that's easy. That's when x equals 0. So the first derivative is undefined at 0. So 0, and then substituting 0 into the original equation, I get a coordinate of 0. So 0, 0 is a critical point. And because the function is defined over the closed interval, we've got to check the endpoints too. So not only do we have to check the minimum, or sorry, this critical point, we got to check the endpoints too. So I'm going to go and take a sneak peek in my calculator. So I'd graph this on my calculator. And this is what the graph looks like with the closed interval from -2 to 3. Ignore those little flat lines on the left. So the graph looks something like this. So obviously, if I look at the graph, I can see, yeah, at 0, 0, that place where the derivative is undefined because there's a sharp point, yeah, it's a minimum. And if I'm looking at my graph, I can kind of see over here at -2, that value looks smaller than the other value over at 3. So it looks like 3 is going to be the maximum value. Well, yeah, I can look at the graph, but I also should be able to look at the values themselves. So I want to test this, and I'm testing this with values of the function itself. So the first value I'm going to test is 0. So 0 has a value of 0. And determine if this is a max or min, I want to check some points on either side. So I can check the value at 1, sorry, at -1, substitute -1 into x to the 2/3. And I get 1. And I substitute 1 into the original function, and I get a coordinate of 1. So on the left side, I have a value of 1, and on the right side, I have a value of 1. And at 0, I have a value of 0. So at that point, I know 0, 0 is less than the 2 points that are on either side, so I know that it is a local minimum. So now, at this point, I probably would have maybe said, oh, I can maybe go all the way to the endpoints to kind of check what's happening. So let me check what's happening at the endpoint. So at -2, I'm going to substitute that into the original function. So -2 to the 2/3, I do need my calculator, and I get 1.5874. And at x equals 3, 3 to the 2/3 power is 2.08008. So at that point, now I can see on the endpoints, one endpoint was 1.5, the other one is 2.0. So at this point, I can say that my absolute minimum happened at 0, 0, and my absolute maximum happened at 3, 2.08. I will say most of the time we're going to be finding where the derivative is equal to 0, not undefined, but I thought this was a unique case and I wanted you to see setting the denominator equal to 0. So we are going to be testing these by testing these with values of the original function. And you'll see with some of my work, with some of these practice problems, you'll see me testing values in the original function. Now, hey, don't forget, when you get equations like parabolas and cubics, you know what those graphs look like. So use that to your advantage. You know what a parabola looks like, whether or not it's facing up or facing down. You know what positive cubics look like and negative cubics look like. So use that to your advantage too in finding maxes and mins. So some simple steps. Finding maxes and mins analytically. So with our algebra, find the derivative of the function, set it equal to 0 or undefined. Those are your critical points. Find the value of the function at each of those critical points. So find the f of those values. Find the values maybe between some of those critical points to see and then to test whether or not they are maxes and mins. And don't forget to test the endpoints if we have a closed interval. We might not always have closed intervals. If I don't have a closed interval, I'm not checking endpoints. So find, let's say I have one critical point. You're just going to substitute in a value on either side of that critical point and just see what's happening with the function on either side. We're trying to paint a picture of what the function looks like by finding critical points and values of the function maybe around it. That's our goal here. So what I have is I'm going to be giving you a couple problems to use analytic methods. In this case, you're going to be doing 4 problems. Take the derivative, set it equal to 0, set it equal to undefined, find the value of the function at those points, and also find the value of the function at the endpoints. That should then start to paint a picture of where the maxes and the mins are. But there's also going to be some functions I'm going to give you that are open intervals. So for instance, number 19, this parabola, hey, surprise, surprise, this parabola is going to have, well, what? A max or a min? Well, it's a right side up parabola. It's 2x squared, so it's going to have a min. I already know it's going to have a minimum. There's no endpoints here, so it's only going to have a local minimum or an absolute minimum. How do you find it? Take the derivative, set it equal to 0, because at the base of that parabola, the slope is going to be 0. So these are going to be pretty easy. The last 4 are going to be a lot easier. Now remember, these cubic functions, I know what a positive cubic looks like, so use that to your advantage as well. All right, at this point, now hop on over and see what my assignment are. I am going to want to see your work for this work, but I'm going to be giving you solutions and textbook solutions to be checking these. So good luck and ask questions.